So what is kinematics? Dynamics, we study kinematics. Now in fluids, we study kinematics. It's the study of its motion without considering the forces or the moments that cause that motion. It's just the study of the motion itself. Then we're going to have two great descriptions. You have the Lagrangian or the Eulerian description of fluids. In a flow field, a lot of times you like to think of, here's a coordinate system, x and y, and you can plot a vector plot. So at this point, there's a chunk of fluid, and it's moving in that direction with that speed. At the same instant of time, but a different location, there's a different chunk of fluid. It's traveling in that direction with that speed. So its velocities are different. And so you can plot different points, and you can put in the vector field. And so this is very useful to describe the field, the velocity field, by a field of vectors. Or you could also put on an acceleration field that every point at that location, at that instant in time, the chunk of fluid that's residing right then and there is experiencing some acceleration. So you could have a vector field for velocity. You could also have a vector field for acceleration. And we really find this useful to describe fluids as they flow. In this geometry, in this region, I can visualize that, this point, this point, this point, this point, this point. Maybe the acceleration's going this way. Kind of as I've shown it, if the acceleration vectors are pointed that way, at the same instant that the velocity vectors are pointing this way, what can you tell me about that flow field? It's decelerating. It's decelerating. That makes sense to you? Let's say you're going 60 miles an hour and then you hit on the brakes. You're decelerating. You're slowing down. In the direction of flow, it's accelerating backwards, decelerating. The equations of motion, F equals ma, or sum of the forces equal to the mass times acceleration, that describes the motion of particles of fluid. The particles of fluid flow through the flow field. This applies for particles, but we like to plot things at points. Points in a grid or points in a region, points in a field. But the point has different particles flowing through it, and the F equal ma applies to the particles, not to the points. Where you could say, let's just track the particles. Let's just track the particles as they flow, and it'll be a lot of bookkeeping, but we'll forget about the grid and we'll just continue to track particles, and then the sum of the forces acting on that particle, we can deal with its current speed and acceleration and then its position. Or you say, let's talk about points, like a field description. F equal ma doesn't apply to the point, it applies to the particles that flow through the points. So this is the Eulerian description. And predominantly we use this description in this class, yet we know that we have to go back to the particles to get F equal ma to apply in our fields. Also, that doesn't mean that nobody's doing Lagrangian description out there in the real world. For an introductory fluid mechanics class, we don't spend a whole lot. We just expose you to that concept and then say you'd need typically a good computer to do all the bookkeeping and then formulate all the equations and then have laws about or rules about fluid particles bumping into each other and getting more compressed, density going up, speeding up, slowing down. True, false questions. Fluid kinematics deals with the description of fluid motion considering the forces and moments that cause the motion. True or false? Because it's not considering. That's how you fix it. So this is false. The Lagrangian description of fluid flow is based on following a fluid particle. True. And then Eulerian description of fluid flow is based on analyzing flow fields. Now we talk about pressure field and velocity field and acceleration field. So I already described this, but how do you and let's say an XY coordinate system, the pressure field, the way you show it typically is lines of constant pressure. It's a scalar field. On maybe the same grid but different plot, you have the velocity field. At every point, you can have your vector representation of what the fluid at that instant in time is doing at that point. What is its speed? What's its direction of motion? And likewise, the acceleration at y and x. So these you plot by contours, and here it's vector fields, vector plots. The book has a number of great illustrations of those. Here's a problem. A steady two-dimensional velocity field is given by, and they use v. Sometimes the bolding indicates a vector, but it's hard to show, right? So bold v or v with the arrow on top, that's a vector notation, is equal to something in the I plus something in the j. The something in the I is minus 0.8 minus 5x. So it's a function of x, but not y. Is it a function of time? No. How about over here? Minus 4 plus 5y. So we have some analytic description of a steady, not a function of time, two-dimensional, x and y, velocity field by this equation. The velocity equals 0 at the location, so v equal to 0. And so what it is just saying that this v is equal to ui plus vj plus wk. I know we don't have a third dimension, but uvw. U is the velocity in the x direction. V is the velocity in the y direction, so this is x direction. V is y direction, and w is z direction. Or aligned with the I, j, k unit vectors. Where is it? Now this is a point. They're describing the x location and the y location of particular points. Where is the velocity equal to 0? A, B, C, D, or E? U has to be 0 as well as V has to be 0. So negative 0.8 minus 5x must be 0. You solve for x. 0.8 divided by 5 with the minus sign, and that's negative 0.16. Likewise for y, so v has to be equal to 0, so negative 4 plus 5y must be 0. That happens only when y is equal to 4/5, 0.8. Now the next question is, for the same velocity field, the velocity at the location 1, 2, and I didn't put the units meters per second, but every one of those has meters per second in it, units. But what is the answer? What is the velocity at the location 1, 2? Well, you'd put in for x, you'd put in 1, and for the y, you'd put in 2. Then you would just evaluate it. So A it is. So if I plotted it, I would, it's hard to do this, but if I'd come out to this location 1, 2, that's in the y and that's in the x, and I would say, okay, I have a vector that is negative almost 6. So I'm going to kind of show it negative almost 6 in the I, and it's positive 6 in the j. Isn't that the vector just like that? Wouldn't that be the v at this point? Negative 5.8i plus 6j. So at that instant in time, now I know it's steady state, so at every instant in time in this flow field, because it's steady state, any fluid particle going through the point 1, 2 is always going in that direction with that speed. If the particle starts at this location, 1, 2, where is the particle 1/100th of a second later? This is 100th of a second. Where is it at? 100th of a second later. Can I pause? And I want to make sure you can do this. All right, so you can tell that if it's in this direction, it's either at this point, this point, this point, this point, this point. Could it be have an x greater than 1? Could it have an x greater than 1? So, I'm down to two choices. Can it have a y less than 2? No. Both of them, okay, now I have to do work. Oh well, I got it down to a 50-50, right? So now what you do is you say, it starts at the location x equal to 1, and it's speed in the xu times the time it's taken for the travel. Doesn't that give me a change in the x? And it starts at the y location 2, and v, which is uvw, the speed in the y direction, times the time that it moves in that direction, gives me delta y. So we calculate u, which is negative 5.8 times 0.01. Negative 0.058 is the delta x. So the new x is 1 minus 0.058. So that becomes 0.942. And then the y, same thing. The new y is the old y. It started at 2. And it travels, I didn't do the computation here. This is 6 times 0.01, 0.06 plus 0.06. So the new y is 2.06. So it's at this new location, 0.9 something, 2 point something. It's the same velocity field, and now you're at this new location, 0.942 and 2.06. What's the velocity at that location? Take that value for x, stick it in, that value for the y, stick it in, and you would compute something. Which one do you compute? A? A? Let me get a couple more A's. Do you see it? It's A. So now the velocity at the new location is negative 5.51 and positive 6.3. What was it at the previous location? 100th of a second earlier, what was its velocity? Negative 5.8 I plus 6.0 J. Now we compare. It's negative 5.51 in the x. See that? So what happened in the x? Did it accelerate in the x or decelerate in the x? So it started at negative 5.8 and it went to negative 5.51. So if I put kind of on a 0, positive, negative, it was negative 5.8. Now it's negative 5.51. Accelerated. It accelerated, positive. The acceleration in the x is positive. Now let's take a look at the y. It started at 6. The speed is positive 6 in the y. And now it's 6.3. Accelerated in the y. The particle velocity changed as it traveled from this location to that location. True or false? True. Okay. The particle did accelerate as it traveled. Accelerate, or sometimes you use that word generally, meaning you could have a negative acceleration instead of forcing it to be deceleration. But is this true or false? It's true. It did accelerate. The particle did accelerate. The acceleration experienced by the particle as it flowed from this location to that location is what in units of meters per second squared? Do you have enough information to make that calculation? Let's just do it in the x. What would it be in the x? It went from negative 5.8 to negative 5.51. So the acceleration in the x would be the velocity in the x, let's use the symbol u, at the t plus delta t minus u at t divided by delta t. Do you like that notation? Does that make sense? Now you make that computation, and I'm going to walk around. When I get 5 correct answers, then I'll move on. Ready? Press forward. So what happens when you put in the negative 5.51 and you subtract a negative 5.8 from that, and then you divide by 0.01 second. Both of these up here are in meters per second. They're a speed, meters per second. You divide by 100th of a second, you get the units, meters per second squared, units work. And the magnitude is 29 with a positive. So that's the x. And then the y, you do the same thing. So the acceleration is a. Let me ask this. Did the particle experience acceleration? It did. It did. It's non-zero acceleration, right? You recall this equation, Newton's second law. Does it apply to each fluid particle as it travels through the flow field? True. Newton's second law, F equal. Does it apply to each point in the flow field? False. That's the false, because a lot of times when you're introduced to this, you say acceleration is equal to dv dt. How many people agree with that? Acceleration, I agree, man, we learned all this. And then you could put that as a vector thing, true? Vector. And then somebody comes along and they give you this vector field equation, and I forget what it was, but it's something xyi, something xyj, the one I just gave you. And then the first thing you do is you say, is there any function of time in here? Is there any function of time in that one that we've been playing with? So they say, I'll take the time derivative of that steady velocity field, and I'll conclude that the acceleration field is 0. And that's not correct. Okay, it's not correct. Particles are accelerating in that steady flow field. The flow field's not a function of time. But we have to get our acceleration correct and apply it in F equals ma to get the right. You're right. So it's, you don't just say the acceleration field is equal to the time derivative of the velocity field. That's incorrect. It's the acceleration of the particle is equal to the time rate of change of the velocity of the particle. That's correct. That's correct. But not of the acceleration field, or at any point in the field, is equal to only the time derivative of the velocity at that point in the field. That's incorrect. So we fix it by introducing what we call a material derivative. If I wanted to say I have a velocity field, and I wanted to get the acceleration of that velocity field, it's so tempting to take the ordinary time derivative. Don't do it. Do a special derivative called the, guess the name, material derivative, and they give it a slightly different notation so that it's emphasized that this is the material derivative of the velocity field. That will give you the correct acceleration field. Let's just do it by definition. The material derivative is, take the, this is a vector quantity right here too. This vector, I'm going to try and emphasize, it's the little arrow over the A, the little arrow over the V. So we get that we have the velocity vector, and we do the, let me back this up a little bit. This V is a function of x, y, z, and t. If I want this material derivative, it's going to be the partial derivative with respect to time plus the velocity vector dotted with del operator. All of that applied to the velocity. This is a partial derivative. Everybody understands that notation, right? So you hold the other variables, space, x, y, and z, as if they're constant, and just do the derivative with respect to the time variable. This is a dot product. You know how if I take two vectors, A vector, B vector, I know how to do the dot product. This is the del operator. The del operator is equal to the partial with respect to x of whatever I feed it, I, plus the partial with respect to y of whatever I feed it, j, plus the partial with respect to z of whatever I feed it, k. It has to operate on something. It's a del operator. I need to feed it something. I need to give it something. But this is a vector by itself, and when I do this, v dot del, it's equal to u partial with respect to x of something plus v partial of something with respect to y plus w partial of whatever with respect to z. All right, that looks pretty abstract there, but it's mathematically correct. Now what you do for this is, if I wanted to flush this out, I would have a is equal to the time derivative of v plus u partial with respect to x v plus v partial with respect to y v plus w with respect to z v. There it is, kind of expanded from its compact notation up here to that. The local acceleration is what everybody readily grasps, that term. It's just our typical, if you didn't know anything else, you'd say, hey, just do the time derivative of the velocity field, and that's your acceleration field. It's not, it's part of the equation. The other acceleration is called the advective acceleration, and the advective acceleration is due to the particle being swept through. And as it sweeps from that location to a new location, does it increase or decrease its speed? Does it accelerate or decelerate? Okay, that's advective. Advective is probably a term you're not used to, but it's being swept. This material derivative has other names. It's also called the total derivative. It's also called the particle derivative. It's also called the substantial derivative, and there's probably other names out there. But guess what? There's consistency in the notation. What's the notation? Big D operating on T. And you can feed it stuff. It operates on stuff. Okay? What can you deal with? Well, you could take the material derivative of a velocity. We just showed that. You could take the material derivative of temperature. What is a temperature field? A scalar field. What is velocity? It's a vector field. And you could also take the material derivative of pressure, and pressure is a scalar field. Let's do this. I'm going to pause. I'm going to quiz you. I want you to write down in 2 dimensions, x and y, what is the material derivative of pressure. Expand that for 2D, x, y, and yes, include time. All right, so the answer for this is the time derivative, and because the pressure is going to be considered a function of x, y, and t, then it's a partial derivative, not an ordinary derivative with respect to time on p, plus u. This material derivative, you have to know the flow field. It's in there. U is the x component of the velocity field, true? Times the partial of p with respect to x plus v. What is this v? Lowercase v. The y direction, right, of the velocity. Partial of p with respect to y. Agree? And if you had 3D, you'd put w partial of p with respect to z. Here's that velocity vector field. It's the same one we've been working with. What is the acceleration field? Now, I didn't give you multiple choice. I got tired of making up incorrect answers. That acceleration field, A, is the, oh, I forgot the name of that funny derivative. And why do they use this D, this big D? I have no idea. It's the material derivative of the velocity field. The partial with respect to time of v plus u partial of v with respect to x plus v partial of v with respect to y. Is it a function of time? No. Let me ask another question. Is this v the same as that v? They look similar when I write them down, but one is lowercase without an arrow on top. One is uppercase with an arrow on top. One is the the y component of the velocity vector. The velocity vector v is ui plus lowercase vj plus lowercase wk. True? uvw. So that lowercase v is the y component of the velocity vector, and this is a vector. So let's work on this, continue it. So we have u. What is u? Negative 0.8 minus 5x. Isn't that u? Times the derivative with respect to x of negative 0.8 minus 5x I plus negative 4 plus 5y j. Yeah, let's continue to write the other one. It's plus v negative 4 plus 5y, the partial with respect to y, of negative 0.58 minus 5i plus negative 4 plus 5y j. That's both of those are on the right side of the equation. So I need to skip down here. I want to put this negative 0.8 minus 0.5x. Now I need to do this derivative right here on all of this. What do I get back? Negative 5 I or not an I? With an I. How about something j? No. Nothing j. Then we'd have down here negative 4 plus 5y times this with respect to y, the derivative of it, that with respect to y. What is it? I plus 5j. Did you follow that step? Or are you lost? Good. Now you say this is going to be, what's 5 times 8? 40.84. Right? So negative 4 minus 5 times 0.5. 2.5x. This 5 times 0.5. It times 0.8. Oh, no, you're right. That's 5. Yeah, that's 5. Thank you. So it's a minus 25. Well, actually, I left it in that form right there, didn't I? I just said, okay, it's take this negative sign out. So it's a negative of negative 0.8 minus 5x times 5. True? So does that look good for the I? How about for the y? So A is the answer. True? Okay. What is the acceleration now evaluated in the field at the location 1, 2? Take this, put in the 1, put in the value 2, and compute it. And what do you get for the acceleration? 29i plus 30j. This math route looks pretty abstract and obscure, but is that the same result as what we got by the 1/100th of a second consideration? Is it the same answer? Can you see what I just did or what we just did? Hopefully you can. So for the velocity vector field, the acceleration field can be calculated as this, which is an ordinary derivative with respect to time. True or false? It has to be calculated with the, what is this name of this derivative again? That's right, the material derivative. Okay. It has to be calculated with that material. What are the other names for this funny derivative, this material derivative? Particle derivative, total derivative, substantial derivative, and there's probably a couple more. Yeah. Now let's consider a problem here. Consider steady. Anytime you see these words, you do know what steady means, right? Not a function of time. Incompressible. Well, like a liquid, or even a gas with small pressure variations, you can approximate it being incompressible. 2D, so we have an x. Notice they show an x coordinate and a y coordinate. All right, where is the origin of the coordinate system they've shown on this illustration? Is it right here? Is that the origin? Right there? That's what the origin is. Okay, and so what are they showing here? This is a converging duct. What are they showing here? It's the upper surface of the converging duct. Maybe it's metal, maybe it's wood, maybe it's something plastic, okay? But the air or the incompressible substance not flowing across it, it's flowing along it. Same with this. This is the bottom surface of my duct. Metal, sheet metal, something, duct. Okay, a simple approximate velocity field is given by this equation. So it has something in the I and something in the Y. It's U naught plus BX in the I minus BY in the J. Just look at that equation for a minute. Is there time in it? But it's a function of X and Y, true? So I could come out to this location. Here is 0, 0. And I could evaluate it. If I evaluate this V at 0, 0, what do I get back? V at 0, 0 is equal to U naught I. So it's completely in the X direction. The speed is completely in the X direction at the location 0, 0. I could come out at this location right here. What would that location be? I don't know, something in the Y, maybe 2, 0, 2. You see that? If you did that, what would be the velocity at this location? I'm just guessing, I'm just trying to say it's 0, 2, right? What would it be? U naught I minus 2B J, something like that, right? Would it be, so it would have a positive X and a negative Y. Is it visualized correctly? Do they have it shown correctly? Well, let's go to this location and evaluate it. That would be, give me the velocity at location 0, negative 2. You'd get U naught I plus B2J. So it would be the same U naught plus. So does that look right? So what's happening is it's in the top half, what direction? It's coming toward the middle. In the bottom half, it's coming toward the middle. True? Can you see that? In the J component of the speed. What about along the center line? It's always straight. It's always completely in the X along the center line. True? All right. Now let's do one other thing. Let's take a look at this location versus this location versus this location. Let's say that location is, I don't know, 2x. And maybe this location's 3x, x equal to 3. So what does the speed look like at the location v is equal to 2, 0? It's along the center line, so y is equal to 0. What does it look like? It looks like what? U naught plus b to b, I, right? Plus 0. If b is positive, guess what? It increased. It increased. Notice the length of the vector shown. This is a vector here. It's got that length visually. At this location, what is the length of the vector? Longer, indicating faster. And at this location, guess what? Longer, indicating faster. True? Okay. Notice that this little bend in the curve, you never put that in. There always are just little straight vectors. So if you want to get nitpicky on this illustration, it's a straight line. Either you put the beginning of that vector at the point where you evaluate the velocity, that's typically done, or you could put it in the middle of the vector, or you could put it at the tip of the vector to start there, right? It could look like that, or it could look like this, maybe like this, or it could look like this. See, you just have to know that the vector, either you're putting your base or your tip or the middle of the vector at that point. What's most common? Put the base of the vector at the point, the beginning of the vector. Yes, sir?
You talked about sweeping. Would that be that vector? Would that be what you're talking about, like sweeping a surface?
Well, it would always be tangent, and if you move along, yes, it's changing direction along this surface. But we always just show vectors as straight little line segments. Don't put an arc to them. So if you look real close, it looks like this is concave upward. We wouldn't do that if it's a true vector. Okay, and this one here, it's just a little straight little vector, right? Vectors don't have curvature. Vectors have, this is a good multiple choice question. A vector, does it have location, magnitude, and direction? Or does it have vector is location, magnitude? Or does a vector have magnitude, direction? Or does a vector have magnitude, direction, curvature? You'll put in curvature too, there's a concave up, concave down, or something like that. Vectors only have two things. They don't have the starting point. That's not part of the vector. You put the vector somewhere, right? But it's not location. Location's not part of the vector. Often vectors represent force at a particular location. But it's not part of the vector. The location is not part of the vector. It's just the magnitude and direction. Got it. All right. Now, this is horizontal speed at x equal to 0. Ignores viscous effects all on the wall. It's a reasonable approximation. Calculate the material acceleration for the fluid particles passing through this duct. What do they want you to do? They want you to calculate that material acceleration. Okay, so they want you to do true, and that's equal to AXI plus AYJ. So give me the components, meaning the scalar AX and the scalar AY, and then represent it by a vector, which is you just put an I there and a J there and add them together. So either way, it's good to do both. Give me AX, give me AY, now give me the expression of the vector A. All right, can you handle that without me doing it? Oh, come on. You can do that? How would you do that? Go back, and what's the formula for the material derivative? With respect to time, that's going to be nothing. Then you add to it U or V dotted del applied to V. And in 2D, that V dot del applied to V in 2D turns out to be U partial with respect to X, U plus V partial with respect to Y, U. That's all our I component. And then the J component is U partial with respect to X, V plus V partial V with respect to Y, J. Need to do that, okay? We'll press forward. Now we go to visualization. We have streamlines, we have stream tubes, we have path lines, we have streak lines, we have timelines, we have too many lines, right? But each of these have particular meaning in them, okay? So streamline, stream tube, path line. These are different if it's a transient flow field. It's changing with time. How many of our real engineering applications in this class, the first introductory class in the fluid mechanics, have really transient flow fields? Very, very, very few. What we have is we have a steady flow field, and the particle gets accelerated or decelerated as it goes through that flow field. Okay, so let's just click on. The actual path traveled by an individual fluid particle over some period is called a, so this is the path traveled by an individual fluid particle. Here it is. It's in a flow field. I drop the particle right there. Boom. It then goes under a path. I think everybody understands what a path would be, right? And if you just, a couple seconds later, time 1 or time 0, a little time later, boom, there it is. At intermediate times, it was there. That's a path, true? So the actual path traveled by an individual fluid particle over some period meaning time, is called a, you pick it. You pick, is it A, B, C? Does it sound like it's a timeline? Streak line, streamline, stream tube, or path line? Okay. A curve that is everywhere tangent to the instantaneous local velocity vector is called a, so here you come out and you have to know the velocity vectors everywhere, right? And then you start somewhere and it's always tangent to it. And then it kind of sweeps and sweeps, you know, it's always, wherever it is, if you evaluated the velocity vector at that location, it would always be tangent to that line. Which one do you think it is? A set of adjacent fluid particles that are marked at the same instant in time, some earlier instant in time, is called. So here I have a flow field, right? I say, you know, this particle and 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 they're all adjacent, right? I mark them at that instant in time. And then later on I say, yoo-hoo, where are you at? And this one went to here. This one went to here. This one went to here. This one. And now that's there at a later instant in time. That's where they're all at. So this represents a line. This represents a line of adjacent fluid particles. They were marked at some earlier time. There's the earlier time. So what is this called? Path line, streamline, streak line, streamline, timeline. Timeline. What was one of these things that really helped you identify that that's a timeline? Earlier time. And now a later time, it's a line of particles. So look at that word. If we come back now to this one right here, okay? This one. I'm now getting 100% correct answers. And what helped clue it in? In the definition, you know, it uses the description of a path. The path line. Locus. Oh boy, we don't understand what a locus is. Are those things that go in herds in the air and they descend on fields and devour the field of food? You know, grain of, what is, okay, let me read the question. Locus of fluid particles that have passed sequentially through a prescribed point in the flow is called a, so here's a point right here. They've passed sequentially through that point. So maybe you're sitting there with an eyedropper. You drip, 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 put in little drops, pop, pop, as markers. So you know then, oh, you know, I'm putting in little red dye. That one goes, and then before you know it, You know, all the previous red dyes that I dropped in that marked that fluid, that's where they're all at. That's now a line. True? What would you call that? The locus is a sequence of locations. Streak line. Very good. Actual path traveled by an individual fluid particle over some period is called a path line. Locus of fluid, we just taught that streak line. A curve everywhere tangent to the instantaneous local velocity vector. That's probably the hardest one, and you had the easiest. Hey, it's all a streamline. That's all, Professor, that's streamline. And then set of adjacent fluid particles were marked at the same earlier time, instant in time, but at some later time they have this curvature to it. That's timeline. Bundles of streamlines that start from a circle of locations or locus. So if I have a flow field that's three-dimensional and I have an enclosing circle, right? And then that point starts its streamline, streamlines. I have a tube. It's an enclosing surface. Now it's flow inside. Okay, that's a stream tube instead of a line. If the flow is steady state, which of the above three are identical? Is it the path line is equal to the streamline is equal to the streak line?
Yeah.
Yes, it is. It is. And so in this class, luckily we don't deal with a lot of transient stuff, and even in reality we have steady behavior, steady flow through our equipment and stuff. So this path line, streak line, streamline, often we just call it a streamline. It's where the fluid particles go. We may use the term streamline, but probably if we had to define it, we'd probably do a good job of defining the path line. Consider the following steady, incompressible, two-dimensional velocity field given. Hey, is that our same old friend? Are we ever going to leave this one velocity field? Generate an analytic expression for the flow streams and draw several streamlines in the upper right quadrant of an XY plot. But show one that goes through this point. Just put one. One will go through there. One streamline that goes through that point, 1, 0. So if you wanted to, you come back over here, you say, here's my X at 1, here's my Y at 2. I'm going to plot a streamline through that point. And which direction did it want to head? In that direction. And so it may go like this. It may go in that direction and curve up. It may go that direction, curve down. I don't know what it does. But you know, you could also, if we just chose that point to start and march time forward, true? You could mathematically choose that point, march time backwards to see where it was previously. And maybe it was over here previously. Or maybe it was down here previously. It's one of those, right? And so that's the streamline. How do I find the function here? This is the y-axis as a function of x. Unless the fluid is doing something like this, guess what? Then I have a very hard time getting y as a function of x. Y is not a function of x if you have this, true? But if they're nice, they give you the streamline such that it can be written as a function where y is a function of x. Do you remember anything about those dark recesses of your mind about description of functions? If y is a function of x, or if f is a function of x, there's only one value of f per x at most. True? And so if this was x right here, you say, well, there's y, there's y, there's y. Or there's f, there's f, there's f. This is a bad function. This is no good. We're looking for y as a function of x. If you had y as a function of x, what would dy dx be? The slope. Dy dx is local slope, the tangent. The tangent. At this point, 1, 2, what is the tangent? What is the tangent to that curve? V. You got it. Who said V? Genius. But that's the missing thing. You got to figure that out. What do you mean V? Well, we had V is something in the X and something in the Y. Can I write dy dt, dt dx? Does that mathematically look okay? It's like, well, if I could get y as a function of time, and then x is a function of time, then I would take the ratio. Well, y as a function of time is v, the y component of the velocity. What is x as a function of time? U. That gives you the right tangent to the curve. So you say, this is getting easy. So dy dx is equal to v. What is v? Negative 4 plus 5y. Divided by u. What is u? Negative 0.8 minus 5x. This equation works. It's mathematically very abstract. But what type of equation is it? First order ODE. I want to solve for this equation. I want to get a... So what do? I separate and integrate. So you get dy, and then you put 1 over negative 4 plus 5y equal to dx, and 1 over negative 0.8 minus 5x. Now it's nasty because I separated, but now what do I need to do? Integrate. All right. You recall that integral of that one, don't you? No, of course we don't. Somebody probably does. What's the form of the integral of 1 over something plus a constant times, natural log. You're very good. So we get the natural log. It'll be 0.2 or 1/5 the natural log of 5y minus 4 on the left-hand side. On the right-hand side, it'll be negative 0.2 natural log of 25x plus 4, and you have a constant of integration. That constant of integration will continue to get morphed. Right away, you can get rid of the 0.2s and just call it a new constant of integration. Okay, so don't get rid of the negative sign. And then you can bring that one logarithm to the other side. So we have the logarithm of 5y minus 4 plus the logarithm of 25x plus 4, some new constant of integration. True? What can I do? The logarithm of x plus the logarithm of y. They multiply, take the logarithm of both. So it's the logarithm of 5y minus 4 times 25x plus 4, all of that equal to constant. Exponentiate both sides, I get another constant. Forget the old constant, it's a new constant. So c is equal to 5y minus 4 times 25x plus 4. Rewrite into a form, y is equal to 4 over 5 plus a constant divided by 5x plus 0.8. Finally got it to look like y is a function of x. Where do I find that constant? I want that curve to go through the point 1, 2. So if it goes through the point 1, 2, then that constant has to be solved, and you find the constant is 6.96. Now I know it. I don't even have a constant. It's one curve through there. So I take that function with this 6 point constant right here, 6.96, and I plot it, and it doesn't look like that. It looks like that. I can evaluate that function at x greater than 1, less than 1. So I did plot it in Excel, and that's what it looks like. It goes to the point 1, 2, right there, and I plotted a sequence of points all the way down to 0. I stopped at 0. At 0, it's somewhere up in 9 something, and all the way out to x equal to 2. And here's the x points and y points. So it's 9.5, and at 1 it's 2, and at 2 it's 1.4444. But that's, what is that line called? Streamline through that point. It was very hard to get it analytically, believe me. it's hard. Now, when you plot things, we've done already the visualization in 2D, the profile plot. Let's say I have a flow between two parallel plates. Over here it's high pressure. Over here it's low pressure. The top plate is not moving. The bottom plate's not moving. The fluid's moving through it. And we would plot the velocity. Here we would plot the magnitude horizontally, right? Like that. So where would that's our velocity profile plot. Where's our velocity, the magnitude, maximum? In the CL. What is this symbol, CL? I don't understand. Center line. Nobody ever defined center line for me. It was like I had to figure that out myself. The C with an L, through it. Guess what? It's simple, right? Center line. That's where you'd have the maximum speed or the maximum velocity. Then you have vector plots. We've already shown them for velocity, field. You have all kinds of stuff. Contour plots, you could have color contours or contour lines. We've done that. Pressure, isotherms, isobars. All this, I think, is all visualization. If you are ever where somebody's showing you something you don't understand, what should you do? Ask a question. But I think most of these are straightforward. All right. Now we have types of fluid motion of a fluid element. Let's say we have an element that starts like this. If the motion later in time was over at this location, it's moved to the right, you would call that its translation. Now, if it's a solid body, it just translates. But in fluids, we're always looking at the rate at which it translates, right? So it's not just meters of movement, it's meters per second. It's a rate of translation. So in fluids, we're looking at very similar things. How about this one? It's just a rotation in solids, but it's a rate of rotation, so many radians per second of rotation. True? Linear strain. Strain, you're changing length over length, but it's a rate at which you're changing that. Okay? So linear strain rate. And then shearing, and then shear strain rate. So these are the four basic types of fluid deformation that you encounter. Make sense? We don't do a whole lot with this. We just expose it to you. Vorticity. Well, vorticity, let me go ahead and stop this so it doesn't do this. Okay, some flows are rotational in nature, and so they characterize the vorticity given by a Greek letter zeta, and the vorticity is defined as the curl of the velocity field. This is the vector notation del cross. Del cross is the notation for the curl. How many people div, grad, curl? Remember that? Divergence, gradient, curl. And so the curl takes in, sometimes it's also written C-U-R-L, takes in a vector field. And it produces another vector field. All right? So this is a vector field here. That Greek letter zeta is a vector field. How do I do the cross product? The del cross. So it's the cross product. Often we have two vectors, maybe A cross B. You learn how to do that cross product. Well, same thing. Use the helpful organization tool of the determinant of a 3x3 matrix, where on the top row you put I, J, and K. representing the little unit vectors in the I, J, K. That's what they are. And then the second row, you put in the AX, AY, AZ in this cross product. But in this case, we're doing del. That's a little tricky. It's the rate of change with respect to X. Give me something so I can do something with it, but that's the I part on the del. Then it's the rate of change with respect to Y. It needs to be given something. And then the rate of change with respect to Z. That's what this del operator is, okay, as a vector. And then the V is just U, V, W, the I, J, K components of the velocity vector field, U, V, W. So there's your little helpful reminder how to compute the curl of the vector field. True? Most of the time you're working in 2D, X and Y, and so the vorticity is equal to only something in the K. This is the only one that survives right here. And it's equal to the rate of change with respect to X of V. That's this. Minus the rate of change with respect to Y of U. That. Minus that. Remember that? I can show you in your Hibbler book where it's at, where they deal with curl if you want to go back and need the review in statics or somewhere else. Or in your Kreisig book or whatever you used in EA. What book did you use in engineering analysis, right? So be able to compute the curl of a velocity vector field. And often it's just 2D XY, and there's often the application. And what we find is that the vorticity is related to the rate of rotation. Omega. Omega is, let's say, the rate of rotation in radians per second. If you calculate the vorticity and divide by 2, the magnitude of the vorticity, that will be the rate of rotation. So it's good to think of and show it to you in a 2D sense, but we'll characterize flow fields as being irrotational or rotational, meaning that the little chunks of fluid in there are either they're being swept along, but as they're being swept along, are they rotating or are they not rotating as they're being swept along? Okay? So you'll see somebody describe a flow field as being rotational or irrotational. Here's a flow field A, and it's like a solid body rotation, flow field A. And so if I look at a chunk of fluid here, a second later it's there, a second later there. And so I look at it be swept around and it's just going in a circle. Okay? How would I achieve this flow field? Put a tank of water on something that's just spinning. You probably never heard of anything like this, but they used to have pieces of vinyl with scratches in them called records. They would put on a turntable. Everybody owned one. Who has ever owned a record player in their life? There's a few hands, a couple more years, there'll be nobody. How many seen one in a museum? I mean, a grandparents' house. Right? But maybe you just put that chunk on there and let it go. And it's not on a turntable, it's going in a circle. Anyway, that would be a solid body rotation in the fluid. If I put a happy face, little floaty right there, that happy face would be turning. Guess what? That flow field is rotational. And if you calculate the vorticity, and notice it's a two-dimensional flow field, the vorticity is always coming perpendicular up, like we did in the last slide. It's IJ is a flow field, it would be in the K direction. Then you find it's 2 times the rate of rotation, solid body rotation. So if you want to know omega, 1/2 the magnitude of the vorticity. How about if we do this flow field? It's a made-up flow field, but it's very fast in the center and drops off as you go out. It's like a vortex. Okay, mathematically, here it is. If you then drop the smiley face on it and watch it, it'll always be looking, it won't be spinning around. It's an irrotational flow field, and the vorticity is equal to 0. Conservation of mass. We've spent some time on this topic now. A lot of it's review if you had a good Thermo 1 background. So consider a control volume in a pipe. It's a very simple system. So here's the pipe, and I'll try and show it just as an introduction, 3D, where you're looking at a little bit of an angle. But the flow comes in and goes out the pipe. True? Now forget the 3D, and let's just cut it, and we're working with what looks like a rectangular projection of the pipe. All right. This is a good control volume. Okay. Where do I have mass flowing into the control volume? On the left face. Where do I have mass flowing out of the control volume? In the right face. Okay. And now if I look at the top, which is really a side, or the bottom, which is really the side of the pipe, is there any flow across it? Is there any in or out? No, it's the metal wall of the pipe. The fluid's skirting along it, but not flowing across it. Okay, so from fluids, or from thermo, if you know the mass density, if you know the average speed, UAVG, maybe you average coming this way down the pipe, UAVG. And I know the cross-sectional area of the pipe. Maybe the pipe is diameter D, and the area is pi d squared over 4. True? Or if you know the radius r of the pipe, then it's pi r squared. But often in engineering, they don't quote radius of pipe. You say, give me a 2-inch pipe. Guess what the 2 inches? Close to the diameter, inner diameter of the pipe. Is it precisely 2 inches? No, but it's a 2-inch pipe. Go buy it and check it out. Get a micrometer. True? 10-inch pipe isn't typically, it's very close to 10-inch ID, but it's not precisely. Somewhere along the line they get precise and then matches up.
This one is rho Q, is that right?
This is mass density rho.
And Q is
And then U is the speed, A, and that's equal to the mass flow rate, m dot. Rho AV. True? Good.
But also, it's equal to rho Q, is that right?
Well, I don't like to use the symbol Q. Some people do. Q would be a volumetric flow rate. A volumetric flow rate. All right? So, volumetric flow rate. I like to use the symbol AV for volumetric flow rate. I know that symbol, not one symbol, it's A times V, and put in parentheses and call that the volumetric flow rate. But instead of introducing another letter that then has been recycled, you're coming straight out of thermo, it's like, oh man, Q is heat transfer. Oh no, slap your head, now it's not. It's volumetric flow rate. Oh great. True? So it's like lowercase h. H is elevation. No, it's enthalpy. Well, what is it? Head or enthalpy or elevation or something? Okay, so that's volumetric flow rate times mass density gives you the mass flow rate. What would be the SI units on this mass flow rate? Kilograms per second, something like that. True? Now there's a term called flux. Flux. If I take the mass flow rate and I divide by the area, what area? That same area right here. This same area. It's the perpendicular. It's the area that the mass is flowing across. Okay? What units do I now get for this term? Kilograms per meter squared second. So it's the mass flow rate per unit area. It's the mass flux. Flux is a common term. And so I don't introduce a new symbol for it, just m dot over A. But look what it is. It's rho U average. Just rho U average. True? So that's the mass flux. Now, when we want to do a more sophisticated job of in and out, what we'd introduce is the control volume, and then everywhere along the surface of the control volume, we're going to have a little unit vector that's outward directed. Okay? How many people have seen this little unit vector that's outward directed? And often that's given the symbol N. It's a normal unit vector. Normal. What does normal mean? It's different than abnormal. No. What does normal mean in this context? Magnitude, okay, yes, perpendicular. It's perpendicular to the surface, so it's normal to the surface, and it's a unit vector. The length is 1. What does it really do? It describes the orientation of the surface at that location. That's what it describes. Here, it describes that the surface, the inside to the surface is over here at this separating the surroundings. So this is the inside of the control surface. The control volume is always inside it. Okay, I'm stumbling on my words here. Here, let's do this. Let's get a new slide. Insert new page. So if I have a unit vector in this direction, n, okay, that means the area is perpendicular to that unit vector. True? And let's do 3 cases where n is here the same. I'm just trying to re-sketch these. And n is here in this one. And this is the area like this. Why do I have 3 cases? Because I want to consider the speed or the velocity at that same location. I want to consider the speed in this direction, v. V, okay? And then I want to consider the speed in that direction, v. And then I want to consider the speed in that direction, v. 1 represents flow out of the control volume. 1 represents no flow in or out of the control volume. 1 represents flow into the control volume. Now, by convention, this n is always outward directed. What do you mean outward directed? Meaning it's pointing in the direction of the surroundings. The other direction that it's not pointing, the opposite direction, is the interior of my control volume. So it tells me the inside versus the outside. The outside is surroundings. Inside, control volume. The focus of the study is inside. So if I look at this, the first case, what's the flow? Outward. And then this is no flow across or crossing the boundary. And then what is this case? Inward flow. Inward. Inflow. Not outflow. Okay? So get those all straight in your mind. Then we're ready to be more sophisticated and talk about not just saying this is m dot in here and this is m dot exit there. We can do one calculation. Okay, so if you want to do a calculation to get the rate of flow across the boundary of the surface, I would do an integral around the whole area, the control surface. What does CS stand for? Around the whole control surface. Okay, the enclosing surface. And n dot dA is the correct direction of the outward directed unit normal vector, times dA is the magnitude of the area. When I sum it up, I get the whole area. If I just stopped right here, if I put 1 right there, that would be the total area in meters squared of my surface, the size of the surface. True? But you want to do a little more sophisticated, n dA. I don't put 1 in there. I want to calculate the net mass flow outward. So if I put in the local speed at every location at the surface, I dot it with the unit outward directed. When it's positive, it will be outflow. True? And if I multiply by rho, that's mass flow rate. This is the mass flow rate out. So if I'm looking along this surface right over here, just this part of the edge right here, the unit vectors are this way, the velocities are that way, right? They're both in the same direction. When I take the dot product, it's the magnitude of one, the magnitude of the other, and either sine or cosine of the angle between. Can you help remind me, is the dot product the cosine of the angle between or the sine of the angle between? Very good. Cosine of the angle between. And the angle between is 0. The cosine of 0 is 1. Okay. So this would all be positive outflow. If I come over here, the unit outward directed normal vector we already talked about. It's pointing in the negative x. But guess what the velocity is doing? It's in the positive x. True? What's the angle between them? 180. I do the cosine of 180 degrees. Not a positive one, but a negative one. So it's the magnitude, negative 1. It's representing not an outflow, it's representing a negative outflow, which is a inflow. Or I should say, it's a negative outflow, hence it's an inflow. So this gives us the right whole thing. So if I compute this and it's equal to 0, then the net inflow is equal to the net outflow. It's no addition or subtraction. If I compute this and it's positive, what does it mean? There's more going out. If it's negative, there's more coming in to the control volume. So that's how you do the surface integral for the, it's a sum of the fluxes over the area. So it's the net outflow. And then the last will be a volume integral because we want to do a conservation of mass. So the volume integral is to tell me how much mass is in the control volume. So the integral over the volume, the control volume, the total control volume, it would be rho. That would be the mass in the control volume. True? Is that a good integral to get the mass in the control volume? That mass in the control volume, don't do where the control volume is deforming in time. Put it fixed in time. This is not, the most sophisticated fluids class you could ever take and make it the most complicated. You want it more complicated? Have a deforming control volume. Ugh. We don't want that. Have a steady, fixed control volume that's not deforming with time. Okay? So if it's not deforming with time, it's really how does the mass density change at different locations as you sum it up to tell you if the mass in a control volume is going up or down with time. Okay? So what is my mass balance equation? Equation would be something like this. The rate of change with respect to time of the mass of the control volume. The only way it can go up is if I have a net inflow. Or it can go down if I have a net outflow. Like that. So we have if you wanted to, you could put 0 is equal to the integral of the control volume, a rho dv, rate of change with respect to time, plus the integral control surface rho v dot n dA. And there is a integral equation for mass balance. When I brought this, to the other side, I got rid of that negative sign in front. Okay? All right. Not to be outdone, if you master the mass balance in a general way, what do you think you can do next? You can do an energy balance for a control volume. All right? And so think about what I had. We have some integral over the control volume of rho u plus ke plus pe dV. What is that? That's how much energy is in the control volume in the form of internal kinetic potential energy. 3 macroscopic forms of energy. Often ke and pe are nil, right? But there you go. Plus the integral of rho u plus ke plus pe, okay, times v dot n dA over the control surface. It's how the energy, internal kinetic potential, is being swept across the boundary or transferred across the boundary of that control volume. And then for the mass, we had nothing that could create mass or destroy mass. But we can have a heat transfer in and a shaft work out of a general control volume. So we could have things which contribute to the accumulation, depletion of energy, as well as the transfer of energy across the boundary of our control volume. That's the energy balance equation. What we do is this work term, if you take out the pushing the atmosphere back as it flows out, or being pushed in, when you bring that term over, guess what that U turns into? U plus PV, H, enthalpy. Enthalpy. Okay? But that's separating out the pushing in and pushing out boundary work terms for the fixed control volume. All right, so what I'd like to do is I'd like to give you a brief overview of the derivation of the Reynolds transport theorem. What do? In all of these things, our conservation laws apply to chunks of fluid, matter, substance. But we like to think about a region in space where the matter sweeps in and sweeps out. The location of the chunk at some time, 0 time, or initial time, or before time, okay? And then later consider some time where it's swept, okay? Then look at the overlap. The overlap is the focus of the study. It's the control volume. And you have a region 1, which is where it's going to be swept into that volume over the delta T. And then you have the region 2, which is going to be swept out of the control volume over the time delta T. If you got that, it's a piece of cake. But that's the hard part, getting all this notation down, because the focus is on a chunk of mass, which at some initial time, T, the chunk, okay, the system is made up of what is about ready to flow into it, plus what is in the control volume. Then at some later time, delta T, T plus delta T, it's made up of what flowed out plus what's in the control volume at the later time. And the amount that's in that fixed region of space called the control volume can change with time. That's why this one is not the same as this one. Now, you say, okay, so it's the system at some future time minus the system at that time. Just write the same thing on both sides of the equation. On the right-hand side, replace the 2 terms with 4 terms. Take and divide by delta T everything. Do the limit of every little group as delta T goes to 0. Recall from Calculus 1, the fundamental theorem of calculus, which is basically the definition of a derivative. And this turns into the time derivative. This turns into time derivative. This is the flow rate out. This is the flow rate in. the way that you would calculate the amount that's in the control volume is do the integral of summing up over the control volume. What do? They introduce a lowercase b. B is the specific property of interest. And the same thing for these in and out. It's a plus because the net flux is positive out, written with this v dot n. What is n again? That lowercase n, unit normal vector that's pointed which way? Outward, outward directed. I'm so thankful that half the textbooks don't have n pointed out and half of them have n pointed in. It's pretty consistent out there. I've not found any book or any paper that has n inward pointed. Okay, they're all outward pointed, which is great. So that's a plus. And now we have the Reynolds transport theorem equation. There it is. And now you could say, okay, if you're interested in applying this to mass, but we have now a general framework where we can apply for mass, where cap B of the system is just the mass of the system. And lowercase specific b, well, it's the mass of the system per unit mass of the system, just one, unity. And what you see is that this left-hand side of the Reynolds transport theorem, it says the time rate of change in the mass of the system. Can I manufacture mass or destroy mass? No, it's zero. So that left-hand side is zero for the mass. And then you just have the integral over the control surface, the control volume, the time rate of change of that integral of rho dv plus the integral of rho v dot n dA. I ran out of room. Okay, dA. All right, so that's the same equation we've had on the previous slide. But you could take this RTT. I forgot. What does RTT stand for? Reynolds transport theorem. And you can put in the big B is the energy of the system. And lowercase b is the specific energy of the system. We like to think of the three macroscopic forms: internal, kinetic, and potential energy. This now, though, on the left-hand side, you think, how can you get some increase or decrease in the energy of the system? Heat transfer, in. Work transfer, out. Equal to, then we have the time rate of change of the specific energy, rho dV, over the control volume, plus, and I'm going to run out of room again, over the control surface. This was a control surface, specific E, rho v dot n dA. So it's the net outflow of the energy. Now, you're saying, Professor, how come I don't have enthalpy show up over here? Because I see that's internal energy U right there. Yes, but you separate out. This W dot has to account for pushing back and being pushed by the boundary work. So you separate that out, put it over, and you'll get the enthalpy. Okay, continuing on. Linear momentum. What is the linear momentum of the system? Maybe you used L in dynamics for linear momentum. It's equal to m times v. What is the specific linear momentum? Okay, if it's m times v per unit m, it's just v. It looks kind of bad, doesn't it? It's the specific linear momentum is velocity. Hold it, velocity is velocity. I know, but you could also interpret velocity as specific linear momentum. Sorry, it's a brain hurt. It's hurting my brain. And so now you can write, using the Reynolds transport theorem, how does the linear momentum increase or decrease? You go back to this equation, sum of the forces equal to the MA. A lot of times they don't write MA. Do they write it as derivative of, with respect to time, of MV? Have you ever seen that? Sum of the forces equal to the time derivative. What's MV? Linear momentum. Linear momentum. And so you can get, this is what you put on the left-hand side. You put the sum of the forces equal to, on the right-hand side, a time derivative of a control volume integral and a control surface integral, where the lowercase b you place by v. What other type of thing? The fourth one, angular momentum. Ew, boy. What symbol, not L with the vector L for linear momentum, what is the angular momentum symbol out of dynamics? I think it could be H. It's not m times v, that's linear momentum. What is the angular momentum? How about r cross something like that? Hey, I haven't looked at it in a long time either. What do you do for the specific? Do per unit mass, so it's r cross v. Now the Reynolds transport theorem is very general, and you could get these balance equations where on the left-hand side you employ something like the sum of the forces equal to the time rate of change of the linear momentum. Here, what is the sum of the what equal to the time rate of change of angular momentum? Moments, r cross f's. Isn't that moment? Sum of the r cross f's, things that make it want to spin, is equal to, and then everything on the right-hand side from the Reynolds transport theorem. Okay, so we covered a lot of material. We're finished with this chapter. Kinematics, what was it all about? Study of motion, not caring about the forces or moments that cause that motion. Eulerian description. Our preferred description, we're talking about vector fields for velocity and acceleration. It makes us use the material derivative, big D. First time you look at that, you say, some editor typesetter really messed up, didn't it? And it's special to fluid mechanics, material derivative. We talked about streamline, stream tubes. We talked about pressure contour plots, velocity profile plots, vector plots, especially for velocity and acceleration. We talked about 4 modes of deformation. We talked about vorticity. Control volume for conservation of mass, conservation of energy, conservation of linear momentum, conservation of angular momentum. And in general, the RTT, the Reynolds transport theorem. Thank you for your attention. We're done for the day.